Thanks everyone for coming. Given that it is now 2 past the hour, I think it is appropriate for us to begin. First of all, I'd like to thank everyone for coming on Friday afternoon for what I think is going to be a really exciting talk by Dr. Felipe Aron. Just to give you a little bit of background about Felipe. So he's currently, he serves many roles down in his home country of Chile. He's a professor at the Pontificia Catholic University in Chile, as well as he not only has kind of a foot in education, but also in basically government service as well. So he has kind of a hybrid career there about that's really kind of both on the educational end and then putting that knowledge into practice through part-time civil service as well. So I think it's a really interesting combination. He has basically woven a path through the United States and then back to Chile. He was one of Rick Allmendinger's students at Cornell, working in the Andes, and then actually came and did a postdoc with me at Stanford for a couple of years, and it was just a fantastic time. And now he's again back in Chile during his journey. I did want to make you aware of a revision to Felipe's talk, in that I think he's going to focus on some of the issues that the SZ4D is really, kind of spans the SZ4D and brings the different kind of components and working groups together. And so his talk title that I'll be giving today is Permanent Deformation and Relief Construction at Plate Boundaries with Emphasis in the Andes. So it seems like it's right up the alley of many of our working groups. And I very much look forward to hearing about some of Felipe's past and then new work in the area, and in particular, how it might be applied to the Chilean Andes. So with that, did I forget anything, Felipe, that's important?
Thank you, George, for the introduction, and everyone at the group for the invitation to give this talk. We have been looking at the new activities that the group is proposing. Your group is proposing there in subduction zones where the country, the Chile lies along the subduction margin of the Andes, so it's pretty relevant. And so we're also really excited to see how that project evolves over time. So I'm also very excited to being able to offer a presentation for you here in this new endeavor. Well, as George said, I would like to apologize for the change in the presentation title, because we discussed with him before that might be better to refocus the presentation on subjects that are more related to the SZ4D group. Originally, I was going to talk about my recent research project I have now, which is focused on the San Andreas plate boundary, not in a subduction zone, although the same principles may apply for subduction zones. So I decided to dig into my early work from my PhD to show you some of the work that we have been doing in trying to address the question of the presentation that George mentioned, which is how the deformation is being transferred from plane boundary to the crust, and with that, how deformation is being accommodated, permanent deformation over time, and how that ended up building up the structural relief that we can observe along the plate boundary. So the slide that you can see here shows the main motivation why I started to study subduction zones and those interactions inside this microsystem of subduction zones, is that when the Maule earthquake happened in 2010, this is a cross section of the plate boundary, more or less at the center of the Maule earthquake rupture. That triggered significant crustal earthquakes in the upper plate, and actually up today, the Pichilemu sequence, which is the one picture with that fault in the upper plate here is the largest event ever recorded for crustal faults in Chile. So the things like we as geologists have long known that that normal faults are the main structural component of the coastal cordillera, specifically along the Andes, and also the constructors of structural relief as well. So we were very surprised to see that we hadn't experienced an earthquake on any of those faults before. We know they are active, and then that just happened after a subduction event. And so also, if you see by the magnitude and the shallow depth of those earthquakes that are shown in this cross section here, the implications of acquiring knowledge about how they behave for society is another main component of what drive me to in the beginning to study those faults. So today I'm going to walk you through a few examples of our own work with my collaborators that shows how the deformation, how we view, how we see those processes of interactions between the subduction interface or any other plate boundary by that matters, and the permanent deformation that's being accommodated in the crust due to the different behavior over time of those subductions at subduction zones on another plate boundaries. So my presentation is divided in 3 sections. The first one, we're going to look at some of that early work I mentioned, in which we analyze the stress transfer between the subduction interface during an earthquake and also during the interseismic cycle using very simple dislocation models. And then we're going to move to some of my more recent work, in which we have been constructing mechanical models to analyze long-term permanent deformation, prescribing plate boundary conditions on those mechanical models, and see how the structures in the crust respond. And finally, the third part, we are going to go over my most recent work, which is currently on review, in which we are using the signature that earthquakes leave in the landscape, in the topography, to invert the processes that raise up that topography, specifically is to invert slip rates on faults based on the morphology of the mountains that have been uplifted by those structures. So before I move forward, I would like to thank many people. I don't have time right now to name everyone, but over these years, all of them in that list and a few others that I might have forgotten, have been fundamental in all the work that I'm showing you here and in general over my education in the States and in Chile. And continued funding has been provided to my collaborators and myself by the Chilean science funding agency, the National Science Foundation as well, and the research center to which I'm affiliated right now, which is called CIGIDEN. This is an acronym in Spanish, but the translation more or less is the Research Center for Integrated Disaster Risk Management in Santiago, in Chile. So let's go over the first part. So stress interaction between those crustal faults at the in the upper plate and the subduction seismic cycle. So what you see here in that slide on the left is a horizontal projection in map view of one of the many slip models that have been provided for the Maule earthquake. In this case, the model by Vigny and collaborators. And to the right, it's a map at the same scale of the rupture, showing with those circles the locations just from the global catalog of the most significant aftershocks, crustal intraplate aftershocks generated by the Maule earthquake. So in red are events that nucleated in the lower plate, so sort of like outer rise events, and actually the largest of those sequences were recorded there, as you can see that beach ball in the southern part of the map. And on yellow, you see the location of the crustal earthquakes triggered by the Maule event that populate some sections of along the rupture, but are mostly concentrated there where the Pichilemu aftershock sequence happened. As you can see, there were at least 2 very large earthquakes, 7.0, 6.9, and a sequence of as aftershocks on that same structure that lasted. Well, I think there's still some seismicity that can be recorded there. And we're gonna zoom into that region here to show you the structures that you can observe in that area. When that earthquake happened, the structural information, geological information in general available for that area was very scarce. So we had to do some classic geology here to reconstruct the architecture and map a few of the rock units to understand better the structural geology of the area. And this is here a map that resulted from that exercise. And then what you can see is that the dominant structural grain, the dominant kinematics that you can see on the faults that populate the coastal cordillera are normal faults, which are mapped here in red. There are some reverse faults as well, but then they are not as persistent as the normal faults. And then also, I hope you can see from this relief. I play a little bit with the color relief map colors that the relief of the coastal cordillera here is very much controlled by the activity of those faults that are interrupting the crust. So the Pichilemu fault, the one that ruptured for that aftershock earthquake, is shown down in the more or less at the center of the map here. Oh, I'm sorry, I'm going to use the pointer here. I forgot we have that tool. So here's the Pichilemu fault, and then that structure doesn't have a decent exposure where you can see the fault plane and other features that allows one to characterize that in a more classical sense in structural geology. But then there are other major structures there that which show enough information as the one that I'm showing here in the upper part of the map, called Topocalma fault. And we're going to see an aerial view of that region in the next slide. So this is how the scenery and the landscape looks like in this area. That cliff here, the coastal cliff here, is about 100 meters high. And I'm going to use a little bit of decoration here just for help illuminating what's going on there. But then that small little hill there and the surfaces that are deformed here have been caused by activity of that normal fault, which is the exposure of that fault is spectacular when you go there. That structure here in that site puts in contact intrusive basement from late Paleozoic time, early Triassic, with young marine sediments, which can go up to the Pleistocene Holocene. Actually, it's not very well labeled in the slide. So it's basically active deformation in sense of active tectonics. So then we ask the question, well, that those events happen after the Maule earthquake, but then what may happen during the interseismic portion of the subduction seismic cycle? How the crust is being stressed and deformed, and which kind of kinematics, which kind of fault types can be excited and enhanced by deformation that occur during the interseismic cycle. So we look at different signals in instrumental timescales, and also we combine that with the signals that we can capture in the geologic timescales, meaning like fault mapping, to try to address that question. And so what you can see here in the map are the most significant earthquakes that were triggered by the Maule event, which are all normal faults and are dominated by that Pichilemu sequence. And here on the, on the right, and here on the left, it's a map that spans in time from 1976 to the day before the Maule earthquake. And so one may, something that you can see from this map is that the number of earthquakes, this is only from the global catalog. There are no local seismic networks involved in this search, but but you can see that the amount of events and the magnitude of them vary in those two phases of the cycle. So in all that number of years, we have only 2 recorded in the global catalog for crustal faults, whereas in the days after the Maule earthquake, we have all that sequence with events being larger. And also the kinematic of those events varies on those 2 phases, predominantly normal faulting after the earthquake and thrust faulting during the interseismic phase. And here we're going to look at surface deformation. So those are all the GPS stations, which are not updated for the most recent that there are there, but then at least for the time of this analysis in the early 2010. On the left, again, we're seeing the deformation, surface deformation pattern expressed in dilatation and strain caused on the upper plate during the interseismic phase of the subduction cycle. And on the right is what happened right after the Maule earthquake and that subduction rebound. So you can see that the contrasting behavior as well, capturing the surface deformation over the seismic cycle, which things being contracted during the interseismic phase of the cycle and extended coseismically. So what about in terms of stresses? What you can see here is in those maps, what you see is a calculation of the Coulomb, the optimal Coulomb stress change for normal faulting specifically. So if the colors in those maps are positive, means that the normal faulting is enhanced. And if the colors are blue or negative, means that normal faulting is not. And so we made a very simple dislocation model, type of Savage type dislocation model, to analyze how stresses are distributed in the upper plate during the phases of the 2 phases of the seismic cycle, and similarly to what we observe on the surface deformation with the GPS, you see a period of compression, in the upper plate, interseismic compression, and meaning that those negative values mean that normal faulting is not enhanced. So the opposite kinematic is enhanced, meaning reverse faulting. Whereas during the coseismic phase of the cycle, normal faulting is very much enhanced, and the magnitude of that, so the larger values of that as enhancement stress on the upper plate is concentrated along a narrow stripe along the coastal Cordillera and outer forarc of the Andes, mainly for this example. And in green, those are mapped normal faults, and the black lines show the trajectories of what will be the orientation of the best oriented normal fault for this specific model. And in cross section, so I'm gonna go back here. So the cross sections are drawn along the blue lines. And in cross sections, you see the same features that we were seeing in map view, where along the outer forarc, tension for normal faulting is being produced during an earthquake like the Maule earthquake, whereas interseismically the opposite happens. So if any fault will be reactivated, will be a thrust fault, not a normal fault. So we put this a simple conceptual model of showing that sort of like pulses of extension and compression of the upper plate, which also have different rates of deformation, because an earthquake deforms like meters per second versus millimeters per year, which is acquired during the interseismic cycle. And then those pulses ended up at the end providing the stresses to deform and move the faults in that affect the upper plate here. And then at least for the outer section of the forarc, we hypothesized that normal faults, extensional features, extensional structures, sorry, are the dominant kinematic, and then the relief that can be that is created along the coastal cordillera is mostly due to the activity of those normal faults, meaning that subduction earthquakes might be the main tool for moving those structures and for making relief at this subscale of deformation along the coastal cordillera. So also of interest of this group, comparing different subduction zones, where else megathrust triggered normal faulting has been observed. And probably many in this audience is very much aware that after the Tohoku earthquakes, sorry for this super simple map, after the Tohoku earthquake, which is, I try to encapsulate the rupture area more or less on that ellipse there, that also was observed along the southern part of the central part of Japan. So in the next slide, I'm going to show you some interferograms that were recorded after the reactivation of normal faults there. And then the magnitude of those events were very similar to what we observe in Maule. And then the difference, though, is that here the earthquakes were able to rupture all the way up to the surface and create important perturbations to the localities that are even generating more casualties as well than the Pichilemu earthquake. Luckily, the events here in Japan and also in Chile, they affected regions which are not very densely populated. Well, that is something difficult to say in Japan, though, but at least in Chile. And then with not significant critical infrastructure. Although, as you recall from the previous map, the area that I show you on those interferograms is right south from the Fukushima nuclear plant, which is shown here by the radioactive sign. So what about the volcanic arc? So we were focused right now in the last slides on the forearc, mostly along the coastal cordillera of the Andes, but also the formation was observed along the volcanic arc. And so with some colleagues at Cornell, we identified some deformation features along the volcanoes. So what you see on this slide on the map on the left is one of the models of the Maule earthquake rupture, and the fringes of the interferograms that we used to measure surface deformation after the earthquake, and then on the right I show you zoom ins into these four regions where we identified that volcanic or unrest signature, which is basically subsidence in the order of 10 to 15 centimeters, and with an approximate length that vary between 10 and 5 kilometers, more or less, of those sort of elliptic patterns of subsidence. And so we hypothesized that the stresses, the tensional stresses, again caused by the earthquake, were responsible of extending and breaking some of the fractures and faults that run parallel to the arc in this part of the Andes, and that allows some fluids on those hydrothermal reservoirs to evacuate the regions, the sections that were broken by the earthquake, and that generated the subsidence. And so where else megathrust triggered volcanic subsidence has been observed? Well, in Japan, also after the Tohoku earthquake, our colleagues there, Takada and Fukushima, identified the same patterns, the same features. And so we both, the two groups published two companion papers for the same journal showing those observations, although they have a different interpretation of what was the reason why those signals were observed after the earthquake in the volcanic arc. And then to finalize the first part of the presentation, we were asking that question until one megathrust earthquake happened. Can forearc crustal faulting trigger the megathrust instead? So the opposite process? Well, in 2014, the Pisagua earthquake sequence happened, and that started with a 15, 16 days long foreshock sequence. And that foreshock sequence started not in the megathrust, that started in a thrust fault in the upper plate, as you can see in the cross section that's labeled by as with the letter C in the right part of the slide, which is this BB prime. So those beach faults that are located up in the upper plate were thrust faults that rupture some of the unknown structures offshore of Iquique in this area, and that happened on the 16th of March of 2014. And then the main earthquake, which is the sleep model published by Ruiz and collaborators in 2014, is shown by the colors on the map of the left. That happens 16 days after the beginning of the sequence in the upper plate. So we did some stress analysis for the same for this sequence, and I'm sorry for this picture, which is not very clear. But then on all the three maps that you see on the right, there is a little rectangle with a green line, which I'm trying to show with a pointer. So that green line is showing the trace of the fault that reactivated in the upper plate, and the rectangle shows the deep extension of the fault. This is an horizontal projection. And so we did some stress analysis, and we found that the stresses that created on the megathrust by the movement of the earthquake in the upper plate generated favorable conditions for the foreshock sequence to start in the plate interface that propagated north, and then ended up triggering the main megathrust 16 days later, which is shown here in the lower map by the location shown here in the lower map by the yellow star. Well, as I mentioned before, I am a geologist, so we again were interested on, well, those thrust faults. When we see them in this part of the Andes. And so what you see here in this slide is a map of Iquique, of northern Chile. Sorry, I don't have a reference map here, but those yellow dots are more or less the cloud of foreshocks and some of the aftershocks of the Iquique sequence. And here's the subduction zone, and you start to see the turning into the Bolivian orocline of the northern part of the northern Chile and southern Peru. And so the lines that are drawn here in the map are actually thrust faults that have been mapped since many years by many collaborators in Chile and the United States and Germany as well. And then as you can see in this picture, in this map, the main orientation of those faults is margin oblique, similar to the orientation of the fault that ruptured during the foreshock sequence of the Pisagua earthquake. So the next slide we're going to see an inclined view, 3D view of this same map, and here it is. And so what you can see in this picture here is that those faults are responsible of shaping the relief of the coastal cordillera in this part of Chile. Different to what I showed you before in the Maule segment, which the mountains along the coastal cordillera were mostly uplifted by normal faults or generated by normal faults. Here in this section of the Andes, those margin oblique faults are the ones responsible of generating the relief of the coastal cordillera. And then just for reference, the Pampa del Tamarugal is the central basin, and then on the left, you can see some of the volcanic peaks of the main cordillera of the Andes. So for having a sense of the scale of this view. And then how do they see in the field those faults? Well, this picture is not from Mars. This is the Atacama Desert, and I didn't want to include any decoration in this picture, just to give you an appreciation, so you can have an appreciation of the scenery, the majestic scenery that you encounter in this part of the world, and then how extreme the hyperaridity is there. So in any study that wants to address problems like problems related to tectonics and climate, here this is sort of like an extreme example of the processes that you can observe and study in this area. And basically, this picture here is showing a few outcrops of faults which are very damaged because the type of rocks there are not ideal to preserve the faults, and also for the specific erosion style of the area, of degradation of the rocks. It's very particular. This is it's a sort of like a salar. And then and all those little hills that you see in this landscape are all of them uplifted in some way by some of those thrust faults, in which have different sizes, of course. And here is another a closer view at the coast of one of those thrust faults that are margin oblique. And this is really a spectacular outcrop. This is this pink red section here shows the damage zone of the fault, and then on top we have a upper Paleozoic, early Mesozoic basement being upthrust here on the lower right of the picture on beach deposits, carbonatic conglomerates and stuff and things like that, which are Paleocene of Paleocene and Holocene age. So here, so you can have an appreciation of how young in terms of active tectonics those structures are, which at least in strike and kinematic coincide with the fault that activated the megathrust for the Maule event. So sorry, the Pisagua event. Whereas margin oblique intraplate thrust faults are ubiquitous and may they trigger megathrust earthquakes. So this map of the Pacific Ring of Fire, in this map I want to focus on the region that I was just showing you for those thrust faults and the Pisagua earthquake, which is here in north of Chile, right south of the Bolivian orocline. Okay. And so a similar feature can be observed right here in Cascadia at the northern border of the United States with Canada. So in the next slide, we're going to compare these two areas at the same scale. And this is what you can see. So of course, the particulars of the two plate bonders here are not the same. Plate rates, type of plates, climate. Of course, this is the rainforest here in Washington, and this is the Atacama Desert. But then the two areas have that feature in common, which is the orocline. So in the next slide, we're going to zoom in there in the Olympia Peninsula in Seattle. And at least from that map, many of the main crustal faults there are also margin oblique. And then if we see those faults in depth, so that white line here shows a simplified location of the cross section shown here on the right, we can see that those are also thrust faults. So this, though we haven't moved on doing specific works on comparing these two areas, but I found this example interesting and for the audience specifically on this of SZ4D. To show you that those two places in the world may have some similarities in that sense, in the style of permanent deformation, even though we are located in a very different climatic and slightly different tectonic setting as well. So now let's move to the second part of the presentation, and in which I'm going to show you some of the simple mechanic approaches that we are using to now quantify and estimate the long-term deformation on those structures, constructing mechanical models of the plate bonding. So the image you see here in the screen is a view of Santiago, which is this basin here, and the urban area is more or less outlined by the pink colors. And on the right is the main Cordillera of the Andes. This part doesn't, and this section doesn't have very many active volcanoes because it's the southern termination of the volcanic gap, but a few are there though. And then at the foot of the western front of the Andes here lies the San Ramon Fault. That structure has been hypothesized that is the main responsible of uplifting the coastal cordillera and thrusting all those rocks on top of the Santiago Basin. And then you can see from the height difference, 550 meters here and 3,200 up there, that over geologic time, that fault might have been responsible for accommodating a lot of deformation in times that range from 5 to 10 million years, more or less. So this is a pervasive feature on this part of the Andes, and it's a thrust fault. This area here is not in the forearc as the areas I was showing you before in northern Chile and in the Maule area. This is right there in the volcanic arc. So what else I need to say? I think that's it. So to build up those mechanical models of the plate boundary, we select domains, and for the example I'm going to show you in the next slides, the green rectangle here shows the extension of the domain that we discretize and parameterize using the mechanical model. And then just for reference and location, that small red line here shows where the San Ramon fault is. And so we built this kind of meshes that we input in boundary elements, mechanical models. And the next slide, I'm going to show you a 3D view of this. So here's the mesh, one of the mesh examples that we have been built for parameterizing crustal deformation in the plate boundary. And then for this example, we, in a forward manner, applied prescribed plate motion. So we pushed the two plates, we made them collide, and then we analyzed what's the response in terms of deformation and slip rates on the many crustal faults that are located along the Andes. I'm just going to show you an example of a single structure in this presentation. And so you see in this numerical sandbox that we built for the boundary element model that the seismogenic zone of the megathrust is being used as a free slip / locked zone, which allows us to compute deformation at the two phases of the seismic cycle in the long term, meaning that at some that the model is free to make that surface slide to mimic the deformation that should be generated during the coseismic period of the subduction cycle. And when we lock that, we can mimic the deformation style generated by the interseismic phase. And then with this model and the geometry of the model and the boundary conditions are all encapsulated in this matrix G here. And then we construct a physical model that relates P, which is plane motion, to S dot, which is the slip rates on the faults that are populating the upper plane in the mechanical model. And so these are some of the results that we obtained for the San Ramon fault. The colors here show have two meanings. The one is the magnitude, and the magnitude is expressed in terms of percentage of convergence rate, and the other is the sign, in which negative or blue means thrusting being enhanced, and red means normal faulting being enhanced. So you see that for the simulations that we produce for the interseismic period, thrusting is the type of kinematics that's being enhanced in that fault, whereas during the coseismic phase of the cycle, normal faulting is being enhanced on the same fault, but then as you can see by the colors, the magnitude of that is almost an order of magnitude smaller. So when we combine the contributions of the two phases of the seismic cycle, we ended up having that thrust motion is mostly enhanced on the San Ramon fault, and coincides, of course, with the long-term geologic kinematic that we can see for that structure. And so So that was expressed in terms of percentage of convergence rate. So what does it mean in terms of slip rates? So assuming 76, 77 millimeters per year convergence rate from the geologic plate motion circuit, those are the ranges that the model is predicting, or model is predicting for the San Ramon fault. And then here on the right, you see what are some of the magnitudes that have been proposed from very limited geologic observational locations of people that have been doing some geologic and paleoseismologic work in this area. And so how you can see there in the slide, the magnitudes are of course not the same, but they coincide more in the range. So the main message I want to express from this short part of the presentation is that this kind of simple mechanical models might be very helpful in trying to address what are the deformation rates of those faults, especially in places where no other no more places where lack adequate pieces of information that can help us to constrain that from real measurements, actually. So now with that, we're going to move to the end of the presentation, to the last part of the presentation, in which for this part, we are basically going to try to respond to one fundamental question. So we'll say that faults move blocks up and down, so they make relief, and that relief eventually is being eroded by climatic forces. So in the topography, there should be information that can, so there should be some pieces of information that can help us understand the behavior of slip in the long term of those faults. So we're gonna address that fundamental question using specifically the morphology that can be captured in the rivers that are carving the mountains that are being supposedly uplifted by crustal faults. And this is that, as you can see in the slide, this is really the title that was intended in the beginning for presenting in this talk. So this picture here shows the San Andreas plate boundary at the latitude of the San Francisco Bay area. In the background is the Monterey Bay, Santa Cruz, Monterey here. That's the Pacific plate. Here's the San Andreas fault. And in this part of the picture is the North American plate, and the most conspicuous feature that can be observed in this area are these mountains here, which are called the Santa Cruz Mountains, and then they form right next to the San Andreas fault in the North American side, and they are supposed to be uplifted by those thrust faults here that run along Silicon Valley, the Santa Clara Valley, which is one of the most important economic and population hubs in the United States. So what ingredients do we need for this experiment? First, we need a measurement of a prediction of the elevation of those channels, and for that we use the power law incision model, and that basically relates the geometry of channels to the elevation of the channel path, assuming that we have knowledge about the uplift rate that's been experienced by those channels and the rock erodibility of the rocks that are being carved by the channel. So in this this equation here, the parameters that are in red are unknowns. So the drainage area, the concavity can be measured just from the DEM, from the topography, but the uplift rate and the rock erodibility, we don't know. However, the rock erodibility is very much related to the type of rocks. So it's way easier to erode a sandstone than an intrusive rock. So we use the geologic map as a proxy to constrain erodibility in this model. And uplift rate, for that, we use a similar approximation of what I showed you before with the BEM model. So we make mechanical models that relate plate boundary deformation to uplift on the surface generated by the slip on the faults that are populating the model. So this matrix H here encapsulates the geometry and the boundary conditions of the mechanical model. V in this case is plate velocity, and U is the uplift rate that might be predicted for that specific model, which enters up here in this equation of the stream power, in the integral expression of the stream power law. So for this last part, I have two subparts. The first one, we're going to quickly have a look at the mechanical and geomorphic model, and then we're going to go straight to the results of what slip rates are we obtaining for long-term slip rates are we obtaining on those faults here. So just for reference, here is the map rotated of this area. Here's the map of California, and the red rectangle shows what is shown here on the map. The San Andreas fault runs right here, and the two thrust faults that I show you in this 3D view before are these two, Perrocal fault and the Shannon Monte Vista. Both are part of the frontal thrust belt system in this area. And then the main reason, and this topography here is the Sierra Azul, and those are the southern Santa Cruz Mountains that I was showing you in the previous slide. So the main reason why those thrust faults are here is because these features, geometric features of the San Andreas faults, those bends here, which are restraining bends, provide localized compression that affects this area, and that is being accommodated by those discontinuities here, which thrust faults, and that at the end produce the uplift of the mountains. So this is similar to popping out of your fingers a watermelon seed. This area has many, it's very convenient in many ways to test this example, test this question that I mentioned before, and set up this model. And also it's interesting because along this section of the Shannon Monte Vista fault, there is evidence of quaternary deformation, and also evidence of a large earthquake, of an historic event that happened in 1865, as I'm showing here in this picture. So here enclosed by the yellow ellipse is the Shannon Monte Vista fault, and this work by Yu and Siegel show what's the using geodetic inversion, show what's the geometry and the kinematics of the earthquake, that the fault that produced that earthquake in 1865. And here on the upper right is a picture of one of the outcrops in a trench that the people at the USGS have been mapping in this area, and here those are very young hill slope sediments that are being thrusting by the Shannon fault here, and this is the one of the branches of the structure as it dropped to the surface. So I mentioned before that the erodibility we use, that we are going to constrain erodibility using the geology. So we have here the river channel points on the map here and below, colored by one of the 21 geologic units that are present in the area. And then here we have a variety of units that range from volcanic rocks, intrusive rocks, sedimentary rocks, and all that mess that is the Franciscan complex as well. And then for the second parameter that is also an unknown for that equation, the uplift rate, we set up a mechanical model. This is again another numerical sandbox that relates plate motion, which is V, in this case separated in the normal and shear component for this box that we set here, to uplift having a specific geometric configuration and boundary conditions, which is of faults, which is enlarged in the inset on the upper left of the slide. So with that, we have an estimation of what the uplift rate is in response to tectonic plane motion, and also the slip rates on the faults. We also have an estimation of how to control for for the erodibility, so U and K, and we set this as an inverse problem, trying to minimize the predicted channel elevations with the observed channel elevations, which are just measuring the DEM, to invert for the erodibility parameters and also the best fit tectonic plate motions, which then we use to calculate the best fit slip rates on the crustal folds. So these are the results. First, I'm going to show you the fit to the data, and the upper map here, the map at the top here is showing the elevation from the 10-meter DEM of the Bay Area. And the central panel, you see in the middle panel, you see what's the prediction of our model, the channel elevation prediction of our model, and then down there is the absolute residual, just the difference between observation and model. And then as knowing all the uncertainties that are encapsulated in this model setup, and acknowledging that we're using geologic data, I think that the results for this the fitting that we are obtaining on the prediction that's shown here by the residuals is fairly satisfactory. So slip rates. The last slide of this part is going to be a view of the fault planes. So we're going to see straight at the fault planes of the Shannon, Monte Vista, and Berrocal faults that are shown in 3D here in this picture. The San Andreas fault is in orange, and this is one of the many attempts of the meshes that we have constructed for this area. And so here on top is this Berrocal Sargent fault, the smaller one, and then the outer frontal thrust, the Shannon Monte Vista fault, is on the lower part of the slide. And then you can what you can see here is that slip is long-term slip due to plane motion in this area is being enhanced in a strike slip thrust fashion on the faults, and that the amount of long-term slip rate varies along the fault and is concentrated in specific parts, like those red patches here, which we are calling long-term slip deficit asperities. So if we have slip rates, we can calculate what's the moment accrual rates produced by those faults. And then if we assume a simple slip predictable model of the earthquake cycle, we can also calculate what's the possible magnitude of earthquakes that can occur on those faults after time passes. And that's what you can see in the table on the right. So according to that prediction of moment accrual rates, that's the magnitude of earthquake that will occur after time passes since the previous sort of characteristic event, or previous significant rupture of the fault. What's interesting about this finding is that the fault that ruptured on 1865, the section that ruptured is right there, is where the slip is being localized as well. And that if we assume that that was the last sort of characteristic event of this area, we are in about 150 years since that time. So according to our model, if that fault moves again, that should be the magnitude of the earthquake, which, as you saw by the setting, probably will cause significant damage on the Santa Clara Valley. So the take-home message from this last part is that coupling mechanical and geomorphic models to estimate landscape deformation, long-term slip, and moment accrual rates, it's very helpful, especially in regions where that information might be missing by traditional analysis. And then those two results, slip rates and moment accrual rates, are a primary input, as you all know, for probabilistic seismic hazard assessments. And so just I would like to take 1 or 2 minutes at the end of the presentation for an extended part of my talk, and acknowledging the formation and consolidation of the group that you have, the SZ4D. I would like to show you some examples and stress a few of the examples that I show you in presentation of why the Andes is an important place for study. And here, as I showed you before, volcanic unrest, the triggering of normal faulting, and also the bending, the orocline, and the specific structural architecture that you can find there. And also along the Andes, climatic variations also produce differences in the behavior of the megathrust as well, in terms of lubrication, the amount of deformation that can be transferred from the subduction channels to the upper plate, and the building of relief, the extension of the rupture of the megathrust, where in places where more lubrication exists, we hypothesize that earthquakes tend to rupture more often to the trench, whereas in places where the sediment is starving of sediments, earthquakes tend to localize in the lower portion of the megathrust, which don't produce very large earthquake, but at the same time enhances more the relief, the uplift of the relief. So this and many of the other examples that you have studied in the past are probably very good reasons to consider this area for an extending study. And in terms of institutional infrastructure, I belong to that center, which is almost 8.5 years old now. We have 150 people there. It's called SIGIDEN. And then this center is divided in 3 main areas. And I work specifically for this area here with research line, natural systems and processes. And that is in charge of supplying the basic science in analyzing those hazards, earthquakes, tsunamis, etc., for the engineers and social scientists, that they can use that for constraining hazards and risk. And so, as this research line, we have been thinking that that the subduction system should be looked as a whole, and then that all the main natural processes that happen there are due to the existence of that specific characteristic plate boundary that we have here. So so this is what I wanted to show more or less in this picture, from coast to mountains here. This is at the area of San Antonio. What we're doing basically now is combining the expertise of all the people that work in this more basic science research line of the group, to try to understand surface processes, deformation processes, and water processes as well, in a intricate manner. So acknowledging what are the specifics that make this part of the world, the plate boundary, and why the result of those natural processes that work here are so are specific and necessary to finally being able to constrain the hazards and exposure of the territory. So we're looking forward to the developments in your group, and also we're looking forward for if you would like to find any ties of collaboration, we are open for that as well. We have a very broad network of collaboration already, so we will be very happy to do so if you ended up selecting this area. And so with that, I would like to end the presentation, and thank you very much for your attention.
Boy, thanks, Felipe, for a whirlwind of really great subjects here. So I think it's time for those that want to ask questions. I know there were some in the chat. I would ask, actually, at this time, I know Harold Tobin has been monitoring the chat for questions. Maybe we'll start with a question from the chat, and then if you have a question live, please feel free to raise your hand in the Zoom so that we can also recognize you after the first of the chat questions.
All right.
So why don't we call on Felipe Delgado if you want to speak up and ask your question, or we can read it if you prefer.
Francisco?
Yes, you can read it, it's fine.
Sorry, I said Felipe. Francisco, yeah.
Yeah, you can read it.
So how do you envision that the megathrust earthquake cycle interacts with the other thrust faults to potentially build the more than 5 kilometers of Andean topography on the geological timescale?
Well, it's a great question. You have many million years to do that, and also what I didn't show in this example of the presentation is that the San Ramon fault on any other fault along the volcanic arc, for example, that's not the only one. So eventually a model needs to be built which incorporates those other structures as well, which are going to be interacting with each other, and those are also going to be enhancing or not long-term slip on the other faults. So I think that if we can assume that the tectonic configuration has been more or less steady in the last 10, 15, 20 million years, so you have enough time for accumulate deformation that can raise up mountains of that height. Also, the contribution of the addition of volcanic materials along the volcanic arc, that also needs to be taken into account. The relief there is not only generated by, it's not only structural, it's not only created by the activity of those faults. Then you have volcanism as well. You have the thermal uplift that can be that's generated on that along the volcanic arc. So there are many pieces here. So what we wanted to make in this investigation was to try to isolate some of them, and then see what's the contribution of some of those specifics. But by no reason, I don't think that we are going to be able to justify the entire formation of the Andes by those simple mechanical models, by the way.
Great,
Yeah.
thank you. Joanne, do you want to go ahead?
Sure. Thank you for that talk, Felipe. That was really fascinating. And now I have to go read all those papers you cited, which I haven't read. But I was wondering, in your model for the San Ramon fault, where it seemed to show that at times in the earthquake cycle, it had a lot of compression along it, and at other times it didn't. Yeah, I think you're going back.
Let me go back to
right. It's past. It's
so,
before all that. Yeah, this
think,
one and the interplate coseismic
I
periods.
animations though. So, sorry, Johan, go ahead.
Yes, this is the picture I wanted to ask about. Do you expect there to be like a hiatus or changes in rate of earthquakes along this fault, and would you ever expect it to actually have a different focal mechanism associated with it compared to what it usually has? Like, is the normal slip basically where you have zero dip slip rate? I guess it's in the interplate coseismic periods. What's happening on that fault?
Well, this is I want to clarify that this is not a fracture mechanics model, and it's not dynamic either. So what is showing here is that it's just the time of enhancement that you produce in the fault only. So if that fault will move with the specific boundary conditions that are that vary across the seismic cycle, that will move in that fashion with that kinematics, and the magnitude of that fault enhancement. It's not related to saying that that fault is really moving, but it's saying that it's more likely if you have more magnitude of slip being predicted. So I'm not sure if I understood your question very well, but then that switch in the kinematics, we don't expect that to see being reflected in the geologic record. So what we think is like is that fault here, which is a thrust fault. When that fault moves in the periods of the seismic cycle in which enhancement for thrust motion will occur. So differently from the faults in the coastal cordillera that I showed at the beginning of the presentation, we think that the thrust faults that are located along the main mountain chain of the Andes, they move predominantly during the interseismic phase of the subduction seismic cycle, whereas the normal faults that generate the relief in the coastal cordillera, they are most likely to move during subduction earthquakes. But then, I'm not sure if I responded correctly to you or to the question that you asked, but I wanted to clarify that this is not predicting that the fault is moving. Actually, it's just saying what is just I want to stress here is that that thrust fault, the San Ramon fault here, which has that imprint in the geologic record as a thrust fault, will probably move during the interseismic period of the subduction cycle. And then what happened during subduction earthquakes is that you are unloading the pushing that happens over time interseismically of that fault. So in some way, subduction earthquakes are contributing to delay the activation of those thrust faults up in the high mountains.
Oh, that's really helpful. No, that's exactly what I was trying to understand, and I appreciate the explanation. Thank you very much.
Thanks, Johan, for the question.
Michelle, would you like to ask your question or have me read it?
I can go ahead and ask it. So, Felipe, great talk, and Felipe, and I particularly thought it was really interesting how you're using the fingerprint of uplift from the channel to invert for slip rate and moment rate. And so, and when you were talking about that, I was thinking about what the role of inelastic processes would be in that mountain building, and in particular, how that might impact those inversions. And so what is your thoughts on the sort of inelastic permanent deformation in this area in its role?
Well, yeah. So inelastic permanent deformation here is being introduced by explicitly putting those faults in the model. So the blocks are not allowed to break by the mechanical properties of the rock. So this is a linear elastic fracture model basically. So there are many other and again I want like to go back to the previous question as well. We're using simplicity in our models for acquiring some information, but then from there to say we're predicting exactly what nature is doing, we're a long way. So simplicity is one of the ingredients that we would like to use to get a clear understanding of all those processes that are contributing to mountain building here. But then the mechanical properties of the rock, of course, are going to be a contributing factor. So meaning that some of those rocks are going to be more easily to deformate than others, and probably relief is going to be more enhanced in these areas. But then at the same time, the resistance of those rocks to erosion is another important factor, which are going to be controlling how high those mountains can be. And then resistance to erosion is not only controlled by the lithology, it's also controlled by the variation in the rain pattern, for example. So if we would like to introduce that into this model, we will not be, if we would like to take that into account, so that expression that I show you here, it's not possible to be built because we need to make K also variable with climate. But then that's why we selected this specific mountain, which is no more than 1 kilometer high. So we are assuming for this model that the variation in the rain pattern, for example, and then the ability to erode rocks differently, it's more or less constant along the mountain. But that's not the same story when you go up to mountains in the, for example, the high Andes or other places. And I think that those other than thermal factors as well, those two are probably the some important components that are not taken into account in this simple view. and which may be important contributors as well to relief building.
Thank you. Kellen has a question.
Yeah, maybe I can rephrase it. The question is very poorly written. What I meant is, can you hear me?
Yeah.
Yes.
Yeah. Oh, yeah.
Thank you.
What I meant is Francisco's question about the mountain building. I thought from what I read, the Andes was built quite a while ago, mostly 10 million years ago or even earlier. At that time, the process, the nature of the plate boundary, do we really know about it? Was it the typical subduction zone like today, and like megathrust earthquake cycles? As Felipe explained, the megathrust earthquake would tend to create tension right in the upper plate instead of building mountains. So the mountains may have to be built with a different mechanism. So I was trying to understand how this the relation between this and today's subduction and the past mountain building. Is there any relation?
Well, you're colliding two plates. So for most of the time, when no earthquakes happen, so you're compressing the plate boundary, and that if you weaken for thermally the area along the high Andes, the plateau where the volcanic chain lies, then you can accommodate that deformation easily. And then basically most of the deformation in the high mountains here is being accommodated in the Argentina, in the eastern part of the Andes. So the frontal thrust there are basically the ones responsible of uplifting the orogene as a whole. But then, well, 10 million years ago, well, the Andes being, the Andes is not only the high mountains. The Andes goes from the trench to the Pampean, to the Forearc Basin in the eastern part of South America. So the things like the sub and this, it's been hypothesized that the Andes being constructed, it's been constructed since the Miocene. Sorry, since since Mesozoic times, Jurassic, early Triassic, more or less. The things like the arc has been migrating, and the style of the subduction zone has been varying over time. I mean, it's almost 100 million years. So you have plenty of time to reaccommodate the plate motion, change the slab deep, and do all those changes as you want. But then the Andes has been slowly constructed since that time. For example, the coastal Cordillera was the volcanic arc during Jurassic times and early Triassic, and then that volcanic arc has been migrating east to the current position. So that migration, and then there are even some steps back to in the direction of the trench. Then when the volcanic arc has been switching back and forth, but then those changes are mostly due to major changes in configurations of the tectonic setting here, and also by major changes on the plate configuration of the planet. So the breakup of continents and changes in the plate velocity and the velocity of the plate circuits, stuff like that. So the things like the current high Andes, so where the volcanoes are right now, that's been in place since at least 20 something million years. Okay, so acknowledging that, so of course some variations in the tectonics in the style of convergence may have been over that time. People here tend to assume that since that time, 15 million years ago to the present, the configuration of the tectonic setting here, the tectonic plate boundary, has been relatively similar to what we can observe today.
Thanks, Felipe, again for a really nice talk. And I think we can all give a big hand to Felipe. If there are no more questions, I think you guys should enjoy your enjoy the rest of your Friday, and Felipe should enjoy himself a pisco sour.
I have it ready down in the kitchen. Thank you very much for the invitation again. So thanks again for the invitation and the time and patience for attending to this talk on Friday evening. And well, I look at, as I said at the end of the presentation, we're really looking forward for your for the future developments of your group, and I wish you the best of luck in what you have ahead. And again, if you any type of contributions that you would like to obtain from colleagues down here in Chile, so we're very open to that, of course. So feel welcome if you need that.
Great. Thank you so much, Felipe. That's great.
Thanks to you.